Good morning, everybody. I hope that you're going to be doing these activities because they're enjoyable and they're great for learning, not because you have to do them for a grade. As you watch the video here that Ms. Guinden has used, I hope you'll take notes from the two different slides that we have. It's not very many notes, and you can use those as we take little assessments just to check for your learning. And enjoy as you learn.
Sound is an example of a wave. Okay, so it's a wave produced by vibrations. All right, right now my vocal cords are vibrating back and forth, and as the air passes by them, okay, that pressure is changing in the air, and that eventually travels to your ear, which interprets that change in pressure and turns it into an electrical signal that is carried to your brain. All right, so just like all longitudinal waves, okay, sound waves are longitudinal waves. They are compressing the air particles together, okay, and that leaves portions of the air with rarefactions, okay, where the particles are spread out. The individual particles themselves might be displaced momentarily, but they return back to their original position after the wave energy has moved through them. So sound waves are carrying energy, not matter, just like all waves. All right, don't be confused. Sometimes we will see the longitudinal waves represented by this pressure versus either distance or time graph, okay, and it looks like a transverse wave, okay, but it is a longitudinal wave, and this is just representing how that pressure is changing with time or distance. Okay, if it's distance, you can determine the wavelength, remember, by taking that distance between two compressions. All right, so just like all waves, sound waves have a frequency and a wavelength. An example of a frequency, a fire truck siren, okay, its compressions, okay, back and forth motions occur 300 times per second. So, I'm sorry, 3,000 times per second, 3,000 hertz. So that's 3,000 times that the particles move back and forth each second. So we'll see that there's a range of frequencies that our ears can perceive, and we'll look at that later in the notes. Sound waves also have an amplitude and a speed, and we'll talk about those characteristics of sound in this lecture as well. Sound waves are mechanical waves, so they require a medium to actually carry the wave energy. So they cannot travel through a vacuum like space. So all of the movies you've seen, like Star Wars, where things are blowing up and lasers are being, emitted with pinging sounds, none of that is actual true to how sound behaves in a vacuum like space. All right, it needs air or water, even solids. Sound can travel through the solid wood of a door. And actually the stronger the restoring forces in the matter that the sound is traveling through has an influence on the speed, and we'll talk. There are a few special terms used for sound waves. The amplitude of sound is referred to as loudness, or commonly known as loudness. So the higher the amplitude, the louder the sound. And this is measured in decibels. And this on the right shows you some of the decibel values for common things that are around us every day. It's important to protect your ears from loud, sustained noises. And so like a rock concert at 135 decibels is right near the exposure limit that becomes intolerable and can do damage to your ears. So be careful with that. The decibel scale itself is a little bit confusing and takes some getting used to. It's a logarithmic scale with a base of 10. So each interval increase corresponds to a nonlinear change in the loudness. So it's not like you can just say, oh, if you have 1 decibel increase, it's, so many times louder. You have to look at ratios and do a little bit of complex math using the logarithm function on your calculator. But if you look at it overall, a change in 10 decibels as far as the sound pressure loudness ratio leads to a 2 times louder sound, roughly. A change in 20 decibels is about a 4 times louder sound, and a change in 30 decibels is about a 16 times louder sound. So very quickly, and that's why they show this as like a conic or cone shape of that diagram, is that the decibel value as you get larger is a much larger increase in that loudness and a higher risk to your hearing. All right, we also have a special word for frequency. Okay, so frequency is referred to as pitch. Okay, a low pitch is like a bass drum or guitar, and something like that is a low pitch. A high pitch is something like that, more like a scream. Human hearing can hear between 20 hertz up to 20,000 hertz, and you'll get to experience what those frequency or pitch values sound like in the lab tomorrow. But your ability to hear changes. So not everyone can hear in this range, but that is the wide range that we can hear in. Infrasonic sounds are frequencies below that range, okay? And ultrasonic sounds are frequencies above that 20,000 hertz. And some animals can hear in ranges outside of that.